Okay, thanks for coming and thanks for trying to organize this. And I promise you, after you go through this review, your score for the thermal section of FE just doubled. Yeah, that's a promise. And so basically, I just go through this. So why don't we first look at, because you realize this is a FE exam. So this is not the exam you take for thermal. You take thermal exam is open book, open notes. Exam problem very similar to the in-class problem, online quiz. So you are going to bring the in-class problem, online quiz, right? Property table. This is the FE exam. So you are going to have the access of the electronic portion. It's a reference handbook. This is the one I got is 9.2. So maybe there's a little bit update. This one is 2013. I don't think the new one will have major difference. So you are going to have something similar to this one. So the key is you need to be very familiar with this handbook. As I go through the example, you will realize the importance of this handbook. So we are going to start from 65. And this one is, we need to know the pressure of nitrogen at 70 degrees Celsius in 100 cubic meter of tank. So obviously this one you need to use the ideal gas equation, right? Because it's nitrogen and the temperature is above room temperature, so obviously it's ideal gas equation. So for ideal gas equation, you need to realize we have the PV equal to MRT, right? Ideal gas equation, and you need to find P. So P is equal to MRT divided by V. And then you need to go to the handbook, page 93. 93. See, page 93, and thermal and physical property table. Over there, you look at this is nitrogen, right? Nitrogen, and then you find the gas constant. That's how you find R, right? And so then the remaining part is just very simple. You put in all this value, and it's 100 kilogram. R is 2968. And the temperature, you need to make sure. For ideal gas equation, you have to convert the temperature into Kelvin. And the volume. So you are going to have the 102 kilopascal. Any question for the ideal gas equation? So this is very straightforward. And 66. This one is a little bit difficult to understand. So the problems said is insulated tank, and by volume, half is liquid, half is vapor. This is saturated liquid and saturated vapor. And then a small quantity of the vapor are going to be released without the addition of heat. you cannot add heat because they already said it's insulated tank. So the idea is by volume, half is saturated liquid, half is saturated vapor, and then saturated vapor are going to be released a small amount of value. So basically, this is state 1, this is state 2. This is the process. You do realize because some vapor escapes, so the total mass are going to decrease. M2 is smaller than 1, right? And you do realize tank, the volume does not change. So basically, this tells us if we look at the specific volume, the end stage, the specific volume will be larger because volume does not change, mass decreased. The definition of specific volume is volume divided by mass. Now, volume does not change, mass decreased, so the specific volume increased, right? So the only thing that can happen is, 1, evaporation of some liquid in the tank. So some liquid become vapor, vaporization. That's how we have the larger specific volume. So this one is a little bit difficult to understand. And 67, this one is air, ideal gas. So basically this one is also another example of ideal gas equation. So you need to understand ideal gas equation is very important in thermodynamics. So anytime you meet the ideal gas equation problem, you should get the full points of the ideal gas equation because it's a very simple equation. All you need to realize is temperature has to be Kelvin, pressure has to be kilopascal. So this one we want to know the specific volume and PV equal to RT. PV equal to RT. So this is another form of ideal gas equation. Pressure, specific volume equal to RT. And we want to know the specific volume. And you do need to realize you need to have the gas constant. Where can you go to find the gas constant? Yeah, that handbook, property table, find gas constant. And then next, you need to make sure the temperature has to be Kelvin, so you need to convert degrees Celsius into Kelvin at 273. And this one, the pressure is already kilopascal, so you do not need to worry about the pressure. And go through this calculation. So that's how you find the specific volume. So you need to understand ideal gas equation is very important. Anytime you meet an ideal gas equation problem, you should get the full points. '68. And the FE exam has a characteristic that is, it's going to provide you lots of properties, but most likely the properties being provided, all this number, 99% of them are useless for this problem. 99%, which means for this problem is that you need to find turbine power, right? So you need to look at the turbine. So which means here, all this information is just useless. All you need to know is asking for turbine, you are going to look at turbine. And you are going to focus on the inlet and outlet. Find some property that is useful. for this case, the work is asking for the power, so the power mass flow rate for the open system. Mass flow rate is very important. And enthalpy difference, H3 minus H4. H3 and H4 both provided. And the mass flow rate, where can we find the mass flow rate? On this diagram here, mass flow rate is 50 kilogram per second. So 99% of the property being provided is just useless, and we just find out the useful one. This one is 50 kilogram per second, and then find H3 and H4. H3, which is the inlet of the turbine, H3, pick that one. H4, outlet of the turbine, H4, pick that one. The unit is already being converted, is kilojoule per kilogram. So you just add, just put in all this value. And go through the calculation. Initially, you have the kilowatt, because that's kilojoule per second. And it's asking for megawatts, so 1 megawatt equals 1,000 kilowatt. That's how you get the correct answer, which is B. Any question for this one? So you need to understand, anytime you look at a problem like this, lots of numbers being provided, but majority of them is useless to solve the question is being asked. You need to focus on the question and go from there. '69. '69. This is asking about for pump for the boiler. Rate of heat transfer occurred in the boiler. So it's asking what happened in the boiler, right? So for the boiler, you first write the equation. Energy conservation equation. And if you do not remember this equation, you can also find it from the handbook. They talk about for the open system, what will be the energy conservation equation. And still, you need to have the mass flow rate and the enthalpy change, outlet, inlet. And the only thing you need to worry about is the mass flow rate. Mass flow rate has to be kilogram per second. This one is said kilogram per hour. So you need to understand 1 hour equal to 3,600 seconds. This is the mass flow rate. So all you need to do is to convert 1 hour equal to how many seconds? And the remaining is just the inlet and outlet is already been provided. The H value for the open system is all about H value. And then you just need to convert kilowatts into megawatts. '70 is asking about which statement is true, and this is asking about the insulated valve. You have an insulated valve, the fluid just goes through it. What's the meaning of insulated?
No temperature from the outside system?
No heat transfer. Q equals to 0. That's the meaning of insulated, which means it's adiabatic, no heat transfer. So which one is true? B. Enthalpy, because this is just a throttling valve problem, enthalpy remains constant. So B is true. And then E, because it's insulated, so E, there's no heat transfer. B and E. Any question for this one? It's a flow through a valve. It's insulated, so it's a throttling problem. Enthalpy remains constant. Like expansion valve in the refrigeration cycle, enthalpy remains constant. So B and E. '71. '71, you do need to go to the handbook because it provided the isentropic efficiency. So you need to go to page 86. Page 86. Look at here. Isentropic efficiency for turbine, isentropic efficiency for the pump. You need to go to look at the handbook, find out the definition of isentropic efficiency. This one is at the pump isentropic efficiency is 70%. So obviously you need to go to that handbook to find the equation. And then you need to realize here inlet of the pump is 10 kilopascal, and the equation you can use based on the handbook for isentropic pump. There's the equation you can use, which is also on the handbook. It's specific volume and pressure difference. So you need to find out the specific volume at the inlet of the pump. For this case, it's that it's 0.01 megapascal. So you need to go to a prop table, which is at page 90. So first, underneath this isentropic efficiency for a pump, it said how to calculate the work required for a pump. Specific volume times pressure difference, right? And then you need to find the specific volume, which is at page 90 here. 90 for steam table. And on the handbook is only provided steam table for the temperature. So the temperature is wrong number, the pressure is not wrong number, but that one, the pressure, what is the pressure at the inlet of the pump? 0.01 megapascal. So it's like 10 kilopascal. So 10 kilopascal, this one, 9.5. This is very close to 10, right? So that's how you find the VF. That's how you find specific volume. So you need to understand for steam table, you need to go to page 90, find the VF because it's saturated liquid. And then all you need to do is to put in kilopascal minus kilopascal. That's inlet pressure, outlet pressure of the pump. Water goes through a pump, pressure increase. And also we have the isentropic efficiency for the pump. If the work required by an ideal pump, isentropic process, actual pump, work required by an actual pump, that's the ratio. Ideally, pump requires small amount of work. It's asking for the actual work. It's asking for the actual power, so you need to have the mass flow rate. Anytime you deal with open system, if it's asking for power, then you have to put in the mass flow rate. The previous two examples both involve mass flow rate. So you need to realize for open system, mass flow rate is very important. How many kilogram per second? And this one is being provided, mass flow rate is still 50 kilogram per second. And then you have this work per unit mass, WA. WA equals to WS divided by the isentropic efficiency of the pump. %, so 0.7, go through this calculation. 71.4. So find the closest answer, which is D. The power required, so this one, the closest one, which is D. So you need to understand, anytime you look at open system, you need to make sure you put in the mass flow rate. And also, anytime you have the isentropic efficiency, you need to go to the property, the handbook, find the definition. Isentropic efficiency for pump has a different equation with the isentropic efficiency of a turbine. (72) is a refrigeration cycle. All the H value has been provided. H1, H2, H3. And also you need to look at the handbook. It tells you which equation you should use. It's asking for the COP. It's the heat being removed divided by the work input of the compressor. So you're going to have H1 minus H4, H2 minus H1. And you do realize H1, H2, H3 is provided. And here, you need to have H4. How do you find H4? Three to 4, that's the expansion valve, so H3 equal to H4. Three to 4 is called expansion valve, so H3 equal to H4. Enthalpy remain constant. Remember the previous question asking for the insulated valve, so enthalpy remain constant. So that's how you find H4. And the rest, they just you put in all the value. And you get the COP. This one, 73. We're still asking for a refrigeration cycle, and you know the evaporation temperature is 0 degrees Celsius, the condenser is 40 degrees Celsius. Calculate the cooling achieved by the evaporator in kilojoule per kilogram. So looking at here, the evaporator 4 to 1. That's why I give you a handout. We didn't go through that property table when we go through thermodynamics. So this one, you can see on the handbook, the steam table is being provided. You can see it's being provided like a table form. However, if you want to find property for the refrigerant, that is the table you are looking at. That is this table. So the refrigerant R134A, it did not provide a property table. At least that was the handbook of the 2013 version said. So you need to understand, you can find a property by reading this handout, which is this property table. The idea is, you first look at this one. This is what we are very familiar with. That's the dome shape. And on the left side is saturated liquid. On the handout, you can see it said saturated liquid. So that's the left slope. And on the right side is saturated vapor. That's the right slope. And this table is called pH table. So basically, vertical axis is the pressure, horizontal axis is enthalpy, which is small case h. Anytime we look at open system, small case h is very important. That's the property you need to figure out. You can see the unit, kilojoule per kilogram. So now let's look at how do we find out the property. So for this one, you need to understand this is at a different pressure and also a protein the temperature. So look at this one, temperature at -10, this is 10. So anytime on this one, that's the constant temperature. So for this case, we know we need to find out, because it's asking for the cooling capacity, so we are looking at QL, small case QL, which is H1 minus H4, because this is what happened at the evaporator. Inlet is 4, outlet is 1. And then we realize $260. So you put in these two values, and you are going to have 140, and that will give you the answer, which is B. So we never really go through this property table in thermodynamics, but it's very easy to understand. And now you know how to find all the H value using that weird form property table for the refrigerant R134A. Because on the handbook, they do not provide the property table for the R134A. They only provided the handout you have. The next one is 74. And this one basically is keep on asking about 3 to 4. So it feels like the process through expansion map, 3 to 4 is the expansion map, is very important. It's asking for process 3 to 4 B, constant enthalpy, because H3 equals to H4, enthalpy does not change. So this one is very straightforward. Definitely not D. There's no way you can have constant entropy and constant enthalpy. If these two are all the same, then 3 and 4 will be one state. Definitely not same entropy. 75. This one is for the psychiatric charge. And we really didn't cover it in thermodynamics, but we covered it from the energy conservation system. So you need to understand, you can go to the handbook. It has two psychiatric charge. And this one is for the SI unit. You can see it's degree Celsius. And there's another one is for the English unit. That's a degree Fahrenheit. And for the problem, it's a unit of degree Celsius. It's asking for air. Obviously, this is the air, and it's asking for at 13 degrees Celsius, 70% relative humidity. What is the dew point? Dew point temperature. You need to understand for the psychiatric charge, horizontal temperature, that's the temperature you read, 10, 20, 15, that's the number. That's the dry bulb temperature, that's the temperature we measured using thermocouple or thermometer. And then this one, that's the specific humidity. And over here, that's also a temperature. And then we have this one. It's at this is 100%, and then you have the 90%. So all this one, that's the relative humidity. So for this one, it's at 13. So you're going to go to look at 13, 10, 12, 13, and you go to look at the 70, and that's the line you have. That's the state. Because you can see somewhere is at 90, 80, 70, and then you have the 13 intersection, and then asking for the dew point. Anytime you ask for the dew point, you need to draw a horizontal line. That's the dew point, and you get here, and then you read the temperature. You go down here, you read the temperature. That's how you find the dew point. If it's asking for the wet bulb temperature, then you need to go to this line. So at this point, it's asking for the wet bulb temperature, then you need to go to a line like that. So the enthalpy remain constant, and then you read the temperature. This time asking for the dew point, just horizontal, go down. So this one is read at 7.6, so it's roughly 8 degrees Celsius, that's why it's B. And the last one in this book is it says the ratio of vapor pressure to the saturation pressure of water at given temperature used to calculate. And this one you need to go to the handbook. Go to the handbook and at page 96, psychiatrics. Basically, this is for the air conditioning, and you can find P, PA, PV. So basically, that question is PV divided by PG. So basically, it's V that is relative humidity. So that's why the answer is A. Relative humidity. That's the PV divided by PG. So you need to know where you can go to find the answer it's asking for, even though you didn't study it. So roughly in that area. That's all the examples from this one. And next, I want to show you what I found from another textbook. And this one, I just want to show you where you can go to find the answer. This one is said helium, compression, isothermal. So you need to go to you need to understand at page 85, that's for the closest sum, and it says the boundary work W. So from the boundary work W, there's constant pressure, constant volume, and then also we cover this is isothermal process. That's a constant temperature, and also this is for ideal gas. That's the equation you can use. There's a natural log. So that's how you find this equation. This is isothermal ideal gas. Calculate boundary work. You have an equation. And the second one here is constant pressure. So obviously, you go back to that page, you look at constant pressure. So this work are going to be pressure time change of volume, right? We already did lots of calculation of constant pressure. See the constant pressure, pressure time change of volume. And this one, isentropic compression. Isentropic compression, and here you go back to the handbook and you are going to find them. Isentropic compression. You're going to find it at page 83. Page 83. Isentropic, basic constant entropy. And there, that's how you find the equation. We cover this in thermodynamics. So that's for isentropic process. So you need to understand where you can go to find the equation. And you do not need to worry about the unit. You can see the unit, pressure unit is very interesting. It's Newton per cubic centimeter. Because here in this equation is just a ratio. So you do not need to worry about the unit of pressure. Just make sure they are consistent. And this one, nitrogen is expansion isentropically, temperature, and find the pressure ratio. And this one, still, you go to this isentropic process, and you find the equation, and you go through, you find the ratio of pressure, right? And this one, the last one, this one is expanded isentropically. It's asking about the work being done by the gas. we didn't cover this part, but all you need to do is to go to the handbook, page 85, and he said here is a special case for the open system. And asymptotic versus ideal gas, you can calculate the work. So that's where you can find the equation. So you can see that that's how this problem being solved. You go to the right location of the handbook, find the equation, and then you just need to put in the gas constant, and you can find the work. So take-home message is get familiar with the handbook so you know where you should go to find the required information. And also we learned a new method you can use to find property for R134A. Because from the handbook, that's the only way you can find the H value. Typically, it's asking for the H using this one. So is there any other question?
Are there any like definitions or like words that automatically, go together? So like isentropic means this.
Asymptotic just means the entropy does not change. Asymptotic. So S1 equal to S2, entropy remain constant, asymptotic. Just entropy remain constant, asymptotic. And the other one, insulated, means there's no heat. And then constant temperature is isothermal, temperature remain constant.
When you did that table, should you waste time interpolating, or if it's really close, should you just pick?
Yeah, you can see I just roughly estimate. Because it's here you have choices for, right? I didn't do any interpolation, just roughly, yeah.